Well, the problems we worked so far, we've been using a gauge pressure. Here's one that'll give us a chance to look at an absolute pressure type of an application, and it puts together several different aspects of fluid mechanics. We'll be applying the energy equation again and dealing with head losses again, be dealing with using absolute pressure, and look at a couple practical problems related to cavitation. And so, well, let's just jump into the problem and go. The problem says to compute the discharge rate that causes the pressure to drop to vapor pressure. And then the data we need, the length of the pipe, diameter of the pipe, and a friction factor is given for us in this problem. And we're going to neglect minor losses in this problem. And the different pressure, atmospheric pressure is given to us and vapor pressure is given to us. Now physically what happens, and this is another classic fluid mechanics problem, and what happens is, and another thing this illustrates is negative pressure that you can, and that's why we have to go to absolute pressure, because we're going to actually have a negative gauge pressure. And what happens if you drop the pressure low enough, and in this system, if we just look at the system, we can intuitively determine that really the lowest pressure point in this system is right here on the downstream side of the pump. And if we drop the pressure low enough, of course, there's a limit. You can't drop it any more than atmospheric pressure, because you'd be down to absolute zero. But even before you get to absolute zero, practically what happens, if you get down to vapor pressure, that's when the liquid water starts making bubbles of gaseous vapor. And then those bubbles can implode, and a problem called cavitation occurs. And you can actually do destruction to the pipe and to the pumping system and so forth. And so in this problem, we're going to figure, and these type problems can be worded differently. In this problem, we're determining a discharge rate. We fix the elevation of the pump, and we want the discharge rate, the maximum discharge rate we can have before cavitation becomes a problem, meaning that we drop the pressure all the way to, well, not quite to zero, but to vapor pressure. Another way of wording this type of problem is how high could you make the pump? How high, for a given discharge rate, how high could the pump be above the water surface in the sump? Okay, so the energy equation comes into play again. We use it a lot in fluid mechanics. And we pick our 2 points. And we always pick the 2 points based on our ingenuity to solve the problem. So let's pick a point here. We know the pressure head there. And let's pick a point here. And we had to use a bit of ingenuity to recognize which point in the system would have the lowest pressure. And what we'll recognize is that we've got atmospheric pressure here, and as we go into here, we convert from zero to a non-zero velocity head. That's going to drop the pressure, and then we're going to have head losses that drop it even more. And then what happens when we come up here, we increase the elevation head, and that's going to drop the pressure head even more. And so that's going to be the critical point there. And so the data that's given here, at this location, atmospheric pressure is given as 13.8 psi absolute A, and that converts to 1,987 pounds per square foot. And the vapor pressure, that pressure at which the liquid water converts to bubbles of vapor, is 73.4 pounds per square foot, and the unit weight of water at this temperature is 62.22 pounds per cubic feet. So that's given. We will need to be able to compute head loss, and so we'll use the Darcy-Weibach equation. We've used it before already in this session. We'll use it again. So head loss is just a friction factor times the length of the pipe divided by the diameter of the pipe times the velocity head. And so that's going to give us the frictional head loss and this length of pipe. The problem statement says neglect minor losses. We could, of course, have easily included an entrance loss there as a head loss as well. Okay, so here's point 1 and here's point 2. We're going to apply the energy equation between those 2 points, and well, let's do that. So here in the surface of the sump reservoir, well, we need to set the datum. That's a convenient place to set the datum, so that's the horizontal datum. And so that's going to let our elevation head at point 1 be 0. And when we worked these problems before, we said the pressure head was 0 because we were using gauge pressure, but we're going to use absolute pressure now, and we're going to set the pressure at atmospheric pressure. And of course, atmospheric pressure divided by the unit weight of water gives you the pressure head. We'll let the velocity be 0 again, and so the velocity head is 0. Now, just generically, we could call that the head at which the pump is vertically located above the sump, Z sub P, and we're going to set this pressure equal to the vapor pressure. And again, the reason we're doing that is because we're recognizing the physical situation that we don't want vaporization to occur. So that's part of the statement of the problem. And then there will be a very definite velocity of flow here, and that's the velocity head. And we've got a head loss, which Darcy-Weisbach equation is going to take care of that for us. As a matter of fact, if we jump back just a second here, Darcy-Weisbach equation, we plugged in the numbers, the given friction factor, the length of the pipe, diameter of the pipe, the velocity squared over 2 times acceleration of gravity, and we were able to convert all of these terms to a number. So the head loss is just a number times velocity squared according to the Darcy-Weisbach equation with a given friction factor. And so that's going to allow us to just simply plug an expression in as a function of velocity for the head loss. And these things we know. We know the atmospheric pressure, we know the vapor pressure, we know the pump is 10 feet above the arbitrary datum there, 10 feet above the water surface in the sump area, and we'll have to compute the velocity. And so when we plug in all the numbers, the only thing we don't know, the only unknown is velocity, and we can solve for the velocity. And when we solve for the velocity, we get Q is V times A. Well, we get 13.2 feet per second, and then to get the discharge, Q is V times A, so velocity times the cross-sectional area of flow in the pipe gives us a discharge of 93.3 cubic feet per second. So as long as we've got a discharge of 93.3 cubic feet per second or less, we don't anticipate the vaporization and associated cavitation to be a problem, but if the discharge got greater than this, it would be a problem. And of course, if the discharge got even greater, you got the other limit. There is a physical upper limit of dropping all the way to absolute zero pressure, which you could never get to. Now, let's work this problem all over again. And so we did it that time with numbers, but this is sort of a classic problem of fluid mechanics that gets worked a lot. And so basically it's just in this format. We've got the pump is some distance above the water surface, the Z sub P, and it very well could be in another problem that you're actually solving for the Z sub P, given that you know the Q. And so if you look at the energy equation, it's going to look like this, and you're going to be plugging in the atmospheric pressure. You're going to be on purpose setting points 1 and 2 so that you can plug in zeros for the elevation head and the velocity head there, and you're going to have these terms, and then it's going to always come out to this expression. And of course the numbers will vary depending on the problem. Okay. We've looked at problems dealing with one pipe, and let's think just a bit about pipes, systems, pressure conduit systems that entail more than one pipe. And to do that, it's going to be convenient to express our relationship between head loss and discharge. And we've worked with this already. And so in Darcy-Weisbach, for frictional head losses in a pipe, we're using Darcy-Weisbach, and we're looked at F for frictional head losses. is this expression we've looked at before. So you could lump all of these terms together and call them whatever you wanted to call them. Let's call them a K. And so we could say that the head loss is a K, and the K is just all of these terms in the Darcy-Weibach equation times Q to some power. And if it's Darcy-Weibach, that power is going to be a square. So this is just a generic expression for a relationship between discharge and head loss in a pressure conduit system. And the K is going to depend upon your choice of equation and the pipe's dimensions and so forth. We also looked at minor losses. We can add in minor losses, and we use this expression, which is that minor loss coefficient times velocity head. And since we know that Q is velocity times area, anytime we've got a velocity squared, we can put an A, replace that with a Q over A, and write the velocity head this way. And so the K would be C divided by 2GA squared. So the point here is that we can write a relationship between head loss is just K times Q. In most cases, in all the equations in the reference manual, there's always going to be a 2 here. There are other equations, Hayes and Williams, for example, another one that would give you a different number, a 1.85 there. But this 2 will be good in all of the cases we're talking about. Okay, so we've got a basic relationship that head loss depends upon the discharge, and then a K that depends upon the pipe characteristics and so forth. And so if you had more than one pipe, the pipes could be either in series or in parallel. And so if you got pipes in series like that, well, if you looked at head losses and discharges, you know, just due to conservation of mass, the continuity equation, that whatever comes out of this pipe goes into that pipe and so forth. So the Q's are going to be the same in all three pipes. What about head losses? Well, if you looked at the head loss is just the difference in head there and the difference in head there, so that the total head loss between those 2 points is simply the head loss in this pipe plus a head loss in that pipe plus a head loss in that pipe. So you just sum up the head losses to get the total. The Q's are the same, and then you sum up head losses to get the total. And you could even express this as an equivalent pipe. And an equivalent pipe would, by definition, just mean it has the same head, and the basic relationship, head loss is K times Q to some power. And an equivalent pipe would be a pipe that has that same relationship. You know, conceptually, if you have that relationship that fits the actual pipes, the same relationship that fits a hypothetical single pipe, and if you did that for a given Q, the head loss in the equivalent pipe would be the head loss in the actual pipe. And so the head loss in the equivalent pipe is just the K in the equivalent pipe times the Q to the power. And then the head loss in the three pipes is just the KQ to the N, the head loss in this pipe plus head loss in that pipe plus head loss in that pipe. First pipe, second pipe, third pipe, each time expressing head loss with that basic relationship. And so all of that just to say that for this equivalent single pipe is just adding the K's together. And so there are fairly simple relationships between pipes in series. And likewise, there's comparable relationships between pipes in parallel. And so if you've got a couple pipes in parallel, it reverses. Remember, when they're in series, the flow rates are the same. But when they're in parallel, the total Q, the Q right here, which by continuity has to equal the Q right there, they're just going to split. The Q in this pipe plus the Q in this pipe is going to equal to the total Q. And what about head losses? Well, the head loss, you know, if you visualize, if these pipes had the same velocity head, all you'd have to do to visualize this is drill a hole, insert a piezometer tube, the water rises to right there, drill a hole, insert a piezometer tube, and watch the water rise up in the tube, and it rises to right there, and the head loss is just that difference. And so what's the head loss in this pipe? Well, it's that difference. What's the head loss? The difference here is the head loss in pipe 1. The difference there is also the head loss in pipe 2. So the head losses are the same in the two pipes in parallel. And if you replace that, if you visualize that as just being one pipe, you could do the same thing we did before, in that for a given head loss, we could relate the Q's, and again, everything is based on the basic relationship: head loss to Q to a power. And so Q, that's our basic relationship. We could solve for Q thusly, and then say that the Q and the equivalent pipe, this is the Q and the equivalent pipe, this is some Q here, would just be this Q plus that Q, and that Q can be expressed in terms of the head loss in that pipe, and that one expressed in the head loss in terms of head loss in that pipe, and all that's just to say that for one pipe with that K is equivalent to those two pipes with those two Ks related by that expression. And so for pipes in series, pipes in parallel, we can have those basic relationships. And one example for pipes in series and one example for pipes in parallel. And here's the same problem we did before. The only difference is before we connected two reservoirs with one pipe, now we connect them with three. And we've got the same 30 feet of difference in water surface elevation, and we got three pipes in series, and each of the three pipes has different characteristics, and they've got different lengths, different diameters, and in this problem they all have the same absolute roughness for use in the Moody diagram to get the friction factor. And so the absolute, and what we're going to do is we'll use the energy equation, except actually in the problem I didn't even bother to write it out because we've done this before. If you pick 2 points, a 1 and a 2, and you write the energy equation between those 2 points, which we did a few minutes ago, you're going to always come out that the head loss is equal to the difference in the water surface, as we did before. So we know the total head loss based on the energy equation is going to be 30 feet again. And so we can use, we're going to neglect minor losses again to simplify the problem and use Darcy-Weibach to estimate the frictional resistance losses in each of the three pipes. So we need a relative roughness. And so for each of the pipes with the given diameters, we can compute a relative roughness, epsilon over D, which is one of the terms needed in the Moody diagram to get the F for the Darcy-Weibach equation. Same story as before. The only difference is there's three pipes now. We need to estimate friction factors, and so we'll estimate the friction factors without the Reynolds numbers and then check them. And then we've reproduced the Darcy-Weibach equation again, same equation we've used already. And to simplify things, we've reduced it down to K times Q squared, as we just talked about. And so given the diameters and lengths and friction factors for the pipes, we can compute the 3 Ks. And given those numbers for the Ks, we can plug into these basic relationships. And so we recognize that the total Q that we're trying to compute is equal to the Q in each of the three pipes. And we also recognize that the total head loss, which we know is the 30 feet difference in water surface elevations between the two reservoirs, is equal to just summing the head losses in the three pipes. And so, and for each of the pipes, we could write out the Darcy-Weibach equation, but for convenience, we're just saying K times Q squared, so we don't have to write the whole equation each time. So head loss in pipe 1 is KQ squared in pipe 1. Head loss in pipe 2 is K2Q squared, and the Q's are the same. And then K3Q squared for the head loss in the third pipe. All those head losses sum up to 30 feet. On the previous page, we computed the K's, which is saying we applied the Darcy-Weibach equation, and we compute the Q. And so it's basically the same problem we had before. We just had to recognize that we're summing the head losses and the Q's are the same in the pipes and made for a little more computational effort. Same thing as the previous problem. Once we compute the Q, we can get the velocities, and then after we know the velocities, we can compute the Reynolds numbers, and then knowing the Reynolds numbers, we can go back to the Moody diagram, which we've been using to confirm the friction factors. So, same type problem, we've just got pipes in series added into the problem. And there are many different problems that have pipes in series and pipes in parallel, and a number of problems are given in your EIT study manual, and there's all kinds of configurations, but if you understand the basic concepts, which we've covered just now, you can apply those basic concepts to handle any type of configuration. And let's do one more dealing with two pipes in parallel. And so here, to simplify the problem, I've gave the K's. These K's can be computed from the Darcy-Weibach equation, and they could even very easily reflect minor losses as well. And so the K's are given, and again, we don't have two reservoirs. What we've got is two pipes. The velocity heads are the same because the diameters are the same. And so if you visualize this as just inserting piezometer tubes and watching how high the water rises, the head drop, the head loss from here to here is just the difference in the water surface in the two tubes. And that's given as 25 feet. Basic relationship, head loss is K times Q squared. And using Darcy-Weibach, K is the expression we worked with already. And I've set up a little table that converted actual lengths and diameters to K's. And we can do that doing what we've already done before. And so just to use, given the K's now, to illustrate the relationships, and basic relationships we've already covered is just applying a little bit of ingenuity to then apply those basic relationships to whatever the problem may require. And so in this problem, we need to compute the discharge in each of the pipes. And so given that head loss. And so we need the relationship. The discharges are different in pipes 2 and 3, so we need the relationships. And so, well, if we go back to the figure, the basic relationships are this. The discharge in this pipe is equal to the discharge in this pipe plus the discharge in that pipe. And the discharge in this pipe is equal to the Q4 is equal to Q1. And then either Q1 or Q4 is equal to Q2 plus Q3. That's the basic discharge relationship. Now the basic head loss relationship is that the head loss in pipe 2 is equal to the head loss in pipe 3. And that's it. That's all we have to recognize. Those are the concepts. And the rest of it is algebraic manipulation, which can take on a lot of different forms depending on how one wants to present the formula. So you got to do a little bit of ingenuity to combine those basic relationships that you know to solve whatever the problem might be. And so the first thing we're going to do, we're going to say the head loss in pipe 2 is equal to head loss in pipe 3. And using that concept, we're going to figure out that the discharges are different, but we're going to relate the discharge in one pipe is just a constant times the discharge in the other pipe. And then after we do that, we're going to say the discharge in this pipe is equal to discharge in the two pipes summed, and that's going to give us a relationship between the discharge in this pipe in whichever one of these we choose. And then having done that, we've got all the relationships between the discharges, and we'll just say that the total head loss from here to here is the head loss in this pipe, and we can go either route. You know, the head loss in pipe 1 plus pipe 2 plus pipe 4 is 25 feet, and likewise the head loss in pipe 1 plus pipe 3 plus pipe 4 is 25 feet. Either way is fine. And let's do that. Having said we're going to do it, let's do it. And so two pipes in parallel, the head losses are the same, and you set them equal. Head loss we always express as a K cubed squared, and the K is from the Darcy-Weibach equation. And so that's going to tell us that Q, once we plug in the numbers from the Darcy-Weibach equation for the K's, we've got a number times Q2 squared equal to a number times Q3 squared, and that's going to give us that Q2 is just a number times Q3. It tells us the relationship between the flow in those two pipes. And then Q1, which is in series with this combined 2 and 3 in parallel. So the discharge in the first pipe is just the summation of the discharges in pipes 2 and 3. And so we can write this, Q1 is Q2 plus Q3, but we know that Q2 is just a number times Q3, and so we can plug that in for Q2. Q2 is just 2.145 times Q3. And I guess I better bring that Q3 down here. Yes. And so after we do that, we get Q1 is just a number times Q3, and I need to fix that and make that a subscript 1. So Q3 is just 0.318 times Q1. Now, the other thing we know deals with head losses. We know that the total head loss from that one point to the other end of the system is just the head loss in the first pipe plus the head loss, and I chose to use the plus pipe 4, and then I chose to use pipe 3 along that path. And head loss is always K times Q squared. The K's are just numbers from Darcy-Weibach. And so we've got 3 unknowns, Q1, Q4, and Q3, but this allows us to substitute in. So where we've got Q3, we can substitute in 0.318 Q1, and we know that Q4 is equal to Q1, so we can substitute a Q1 in for Q4, and then when we do that, there's only one unknown left, and that's Q1. And then we can solve for Q1 and get the discharge in one of the pipes. After you know the discharge in one of the pipes, then it's just a matter of going back to these relationships. We know the discharge in pipe 1 is 4.47 cubic feet per second. We plug that back in to get the discharge in pipe 3, which we can plug back in to get the discharge in pipe 2. Okay, so the basic relationships for pipes in series and pipes in parallel are there. We've just discussed them. Then the format of the problems can change, but you apply a bit of ingenuity and some algebra to apply those concepts to solve problems. Okay, let's look at another type of an application related to what we've done already, and that's dealing with pumps. And we've already applied the energy equation to look at pumping water from one level to another. And to add one other concept to that, and that's the concept of a pump characteristic curve. And if a pump characteristic curve totally characterizes the pump, and so there's basically 2 aspects of this problem. One aspect deals with characterizing the pump. The other aspect deals with characterizing the pumping system. The characterization of the pumping system we've already done earlier in this session, and so we're just going to take what we've already done and add it to one other concept, and that's characterizing the pump. And we did an example earlier in which we pumped water from one reservoir to another, and we computed the pumping head required to do that. And having done that, the next logical question is, will a pump do it? What pump does it take to provide this pumping head? Well, when you think in terms of pumps and their capabilities, there's a relationship, again, between head and discharge. If the pump has to work against a small head, it can pump a lot of water. But if you're asking the pump to lift the water some enormously great vertical distance, it's not going to be able to do so at a large discharge rate. And so what this curve says, and this would be given in the problem, because it's for a given pump. It's determined by the pump manufacturer. And it says for this given pump, if this pump has to overcome 160 feet of head in this example, the discharge rate's 0. That's it. But if there's not so much head, if the head decreases, it can pump greater discharge rates. So we're looking at discharge versus head. And of course this head-discharge relationship we talked about with head losses. Now we're talking about it on the reverse side, on the pumping side, not losing head but adding head to the system. And so that's a head-discharge relationship which can take various forms. Here we've shown it graphically. And so what we want to do now is take this additional information that characterizes a pump and add it to what we've done already. Now this is what we've done already. Let's redo, repeat, review what we've done already. We've said that if you're pumping water from one location to another, we can write the energy equation between point 1 and point 2. We write the energy equation. We substitute in the terms as we've done already. The Z we draw through the water surface and the downstream side of the pump. The pressure head 0, we're back to using gauge pressure again. The velocity head 0. The head provided by the pump. The elevation here is Z2, 0 pressure head, 0 velocity head, and we plug in the head loss. Now once we do that, that tells us what we could have intuitively determined and have earlier, is that the pump has to provide head for the lift, the Z2 minus Z1 we can call the lift, plus it has to provide for the head loss. Now the delta Z is a fixed number set by the physical configuration of the system. The head loss is a function of discharge. As we already talked about, head loss is some K times a discharge raised to a power. So this is a function of a discharge, and the pump characteristic curve is a function of discharge. Head is a function of discharge. So we've got two head-discharge relationships, one characterizing head loss, one characterizing the capabilities of the pump. And so here we're just looking at the pumping system. The pumping system is described by this relationship. And so if we go back to our example problem, and the example says two reservoirs are connected by 850-foot long, 6-inch diameter pipe, and the friction factor from the Moody diagram is given, and a pump with the given characteristic curve is used to lift water from one reservoir to the other, determine the discharge rate. Okay, let's do the part that we've done in previous examples, and that's relate the system head curve, we call it, relating the characteristics of the system independently of the pump. And so we use the energy equation just now and determine from the energy equation that the head added by the pump, that term in the energy equation, is going to have to take care of the delta Z, and it's going to have to take care of the head loss. We need an expression for the head loss, so we plug in the Darcy-Weibach equation, same equation we've used before, and then we plug in the numbers that we know, the friction factor from the Moody diagram, the length of the pipe, diameter of the pipe, the Q squared is an unknown, divided by 2g, the acceleration of gravity, and the area, which we can compute from the diameter of the pipe. And we've got an expression that says that the head required of this pump is 100, and that's that delta Z plus the head loss. The head loss is just a number we computed from the Darcy-Weibach equation times Q squared. And so that's what we've done before, except now we don't know exactly what Q is going to be. And so if we wanted to do this, to illustrate it in the graph, we would just say for different Qs, and the graph's in gallons per minute, so the Qs are in cubic feet per second, conversion factor. We can plug in the Qs and get the pumping head. And we just computed these points. And those points represent the system taking the concepts that we've used in other examples just a little bit further. And then the pump itself is characterized, and this would not be computed, this would have to be given. It's determined in a laboratory. And so what would the discharge be? Well, both of those are good relationships, and this is the point in which they're both valid. And so that point would set the discharge rate. Okay. Well, let's go to one other topic in fluid mechanics. We've been dealing with pressure conduits, and there's one open channel flow equation that's included in the reference handbook in fluid mechanics, and that's the Manning's equation. And so we want to at least look at the Manning's equation. And so let's work our way toward the Manning's equation, present the Manning's equation, and then work example using that equation. And so just in general, by introduction to open channel flow, and open channel flow is where we've got the liquid with a surface at atmospheric pressure as opposed to pressure conduit flow. The flow can be either uniform, meaning all the flow characteristics are constant along the length of the channel, or they can be non-uniform varied, meaning flow characteristics vary along the length of the channel. And then the flow could be steady, meaning the flow characteristics are constant over time, or unsteady, meaning the flow characteristics change over time. And the whole field of open channel hydraulics and fluid mechanics applied to open channels would address these different types of problems. And the formulas that we're given in the reference handbook is for uniform steady flow. So we're going to focus our attentions on steady uniform flow and stop with that. And so uniform flow means that the depth, the cross-sectional area, the velocity, the discharge at every section are constant. So if you picture a channel, whatever shape and form it may take, uniform flow means that all the flow characteristics are the same along the length of the channel. And then if you visualize the energy diagram, that means that the slope of the energy line, the slope of the water surface, the slope of the channel bottom, they're all parallel. And definition, normal depth is just the depth at which uniform flow occurs. And so we're planning for open channel flow problems on the exam to limit themselves where we recognize that this is a uniform flow problem. And so we can use the one equation that's provided in the reference handbook, and that's Manning's formula, to deal with flow situations as far as a uniform flow equation. Now, energy equation, the basic concepts are equally valid to uniform open channel flow as well as pipe flow. And so here's Manning's equation. This is an empirically determined equation that's been around for many decades. It's a flow equation, and so it can be written in either English units or metric units. The difference between the English units and metric units is one constant. This is not a dimensionally consistent equation. This is an equation that you have to use the right dimensions, and so velocity has to be in either feet per second or meters per second. And N is a given roughness coefficient, which is comparable to the friction factor in the Darcy-Weepock equation. The hydraulic radius, by definition, and is the hydraulic radius is the area flow divided by the wetted perimeter, and we'll look at that in just a second. And then the slope, that's the slope of the energy line, but recognize we're dealing with uniform flow, so the slope of the energy line can be estimated as the slope of the channel bottom. So if you're given a slope of the channel bottom, that's the S. And, well, the equation we're used to using is the Q is velocity times area. And so if you multiply both sides by A, you put in an A there and an A there, you write the same equation in terms of the Q. And so the Q needs to be in cubic meters per second. So Q needs to be in cubic meters per second or cubic feet per second, the A in cubic square meters or square feet, the hydraulic radius in either feet or meters, and of course the slope term has no dimensions. And so that's the Manning's equation. Now, a lot of using the Manning's equation is just a matter of geometry. And you have some problems in your manual that deal with the geometry of applying Manning's equation. And let's use this geometry as an example. That's you'd rather have a rectangle, but a trapezoid you can work with easily too. And so just going to geometry, and one definition is wetted perimeter. And here's the wetted perimeter. It's the length. If you visualize a plane being placed perpendicular through the flow, that would be the intersection of the plane with the boundary of the flow with the container. And so that's the wetted perimeter, and the flow area here to plug in, or the flow area here to plug into Manning's equation just from geometry would be the top width plus the bottom width divided by 2 times the depth. So we're really out of fluid mechanics into geometry, but geometry is a big part of solving fluid mechanics problems. And so just taking the top width plus bottom width, dividing that by 2, and multiplying by the depth. That would give you a cross-sectional area of flow. And then just from knowing the side slopes in geometry, you could get the top width. Bottom width is, in this example, is given as 20 feet. So if you take 20 feet, and then this portion of the top width is side slope of 2, 2 times 6. There's another one over here, so we multiply by 2 to get the top width. And then the top width plus the bottom width divided by 2 times 6 feet gives you 192 feet squared for the cross-sectional area of flow, which we'll need to plug into Manning's equation. As a matter of fact, the geometry is going to take us more time than actually plugging numbers into Manning's equation. The wetted perimeter, and of course it would be easier if it was a rectangle, because then it would just be the bottom width plus twice the depth. But would make it a little more complicated by using a trapezoid. The wetted perimeter would just be the bottom width to get this portion of it, and then this portion of the wetted perimeter would be, well, that's 12 feet. So 6 feet squared plus 12 feet squared, take the square root of that, Pythagorean's theorem. It gives you that length. You've got the same length over here, so you multiply by 2, and that gives you a wetted perimeter of 46.8 feet. And hydraulic radius, by definition, is area divided by wetted perimeter. And so we take the area and divide it by the wetted perimeter to get the hydraulic depth of 4.10 feet. And well, for this problem, we'll stop right there. With another definition would be hydraulic depth, which is area divided by top width, and we could compute that as well to be 4.36 feet. So we know about this geometry, and you've got some examples in your manual that deals with trapezoids, and of course a rectangle you can do a lot quicker because the geometry is a little easier for a rectangle. So this problem says compute the discharge in a concrete. In concrete, we've got an N of a 0.015 channel with a previous cross-section and slope of 0.1%. And this just gives us a problem to plug the numbers into the Manning's equation. And so we reproduce the Manning's equation here. Having gone through the geometry, we can plug in the cross-sectional area of flow, which we computed on the previous page. We can plug in the hydraulic radius, the longitudinal bottom slope for S, the roughness coefficient N, and compute a discharge of 1,540 cubic feet per second. Now, that's the easy way to apply the Manning's equation. And that's the way I would anticipate problems being on the exam. The other type of a problem, which is just as easy conceptually but takes a little more computation, is this example. And in this example, the discharge is given. So either the geometry is given, you compute the discharge of the previous example, which is a direct solution, or conversely, the discharge is given and you want to compute the depth. And this is a design type problem where you've got a channel conveying water, you know the discharge, and they ask you how deep does the channel have to be to convey this discharge. And so in this problem, we're given that the discharge is 400 cubic feet per second, the longitudinal bottom slope is 0.0016, and the roughness coefficient is 0.025. And so we've got those numbers to plug into the Manning's equation. And so we reproduce the Manning's equation, except we're trying to compute depth. You don't see depth, but you recognize that the area and the hydraulic radius are both a function of depth. And so we put the unknowns on the left of the equal sign, the knowns on the right, to go through the arithmetic manipulations, the algebra. Plug in the flow rate, plug in the roughness coefficient N, plug in the constant 1.486, the slope, and we get AR to the 2/3 is 1.68.2. And now we've got to express A as a function of depth, which we can do just from the geometry of a trapezoid, doing the same thing that we just went through on the previous example. We expressed area as a function of depth. We expressed the wetted perimeter as a function of depth. Hydraulic radius is area divided by the wetted perimeter, all expressed as a function of the depth. And so now we can plug this expression in for the cross-sectional area of flow. Plug this expression in for the cross-sectional area of flow. Plug this expression in for the hydraulic radius, and that's going to be equal to 168.2. And when we do that, we've got an expression in terms of y, and we can solve for the depth y and get 168.2. And by trial and error, that comes out to 3.36 feet. And then from that, we can we've got the depth. If we wanted the velocity, we divide the discharge by the area to get the velocity. And so that's basically using the Manning's equation. The geometry is a little more complicated in a trapezoidal channel. A rectangular channel simplifies the geometry. And so the problem can be given for a given geometry, compute the flow rate, or vice versa for a given flow rate, compute the geometry. And that concludes the fluid mechanics portion of our review. Again, the key to this subject, like all the other subjects, is to work on a lot of problems, and so I encourage you to do that. I do look forward to being able to visit with you at the question and answer session, which will be live through the video system later, and good luck on the exam. I know you're going to do well, and good evening.